Just a quick review on significant digits, because every time you do a calculation in chemistry, that calculation is typically based on data, and your data is limited by the precision of the instrument you used or by your own judgment. And so when you're using that data to determine a final answer, because typically, for example, we collect data that we actually use for something else, okay, for a different type of measurement. So for example, like, we don't have a device that measures moles specifically, but there's a relationship between grams and moles, and we have access to scales and balances that measure grams. And so some scales and balances are very specific and maybe go, like 4 or 5 digits past the decimal place to like the 10,000th place or the 100,000th place. And then other ones are not as precise and they maybe only go to the 10th place. Because there's differences between the instruments, then we have to make sure that our final answer that we're coming up with based on those pieces of data does not exceed the precision of the original data. Okay? And as you know, when you put numbers in a calculator, what happens is the calculator doesn't think about that. It just, if it's not, a number that like ends at 0.5 or something like that, then what happens is you end up getting several numbers after the decimal place going across the screen, because that's the mathematical answer. But for science, you need to have an answer that's reflective of the precision of your instruments, and that's where SIGDIGs come in. So just a very quick review here. All right, there are 5 rules for what is significant, okay? The easiest thing to get out of the way is non-zeros. So anytime you see a 1, 2, 3, 4, 5, 6, 7, 8, or 9, anytime you see one of those numbers, that is a significant digit. All the rest of the rules have to do with zeros, and they have to do with where the zeros are. And so I'll just take a couple minutes to review. Any zeros between other significant digits are significant, okay? So if you have a 0 in the middle of a number, then that 0 will be significant. Rule number 3, all zeros to the right of the decimal place and after a significant digit are significant, okay? So anything to the right of the decimal place and also after another significant digit. All zeros to the left of the first significant digit are not significant. And the thing that I would add here, just for clarification, is that they are placeholders. And I'll talk to you in a minute about what that means and try to make that a little bit more obvious to you. Okay, so they are placeholders. And then zeros that are at the end of a whole number are not significant either, because in all likelihood that number was rounded to that whole number, and that's why they're not significant, because you can't rely on them. You can't know for sure, like, was that a real 0? Did it land exactly on that number, or was it just around that number and they rounded, okay? All right. So I just want to go through 2 examples to kind of drive these points home here, and we'll talk about which rules apply. So the first example that I want to go over is the difference between 70, just 70, and 70.0, okay? 70, I would describe as a whole number, right? Okay. And if we're counting significant digits, well, then the 7 is definitely significant because of rule number 1, right? Which is that all non-zeros are significant. So the 7 is significant by rule number 1. The 0 is not significant because of rule number 5. Okay, so if you look at this, that 0 is at the end of a whole number and there's nothing after it. There's not a decimal place, therefore it's not significant. All right, let's compare that to 70.0. 70.0 seems like a precise number. It indicates to you that they did not round to 70. They mean 70.0 on the dot, okay? So for that reason, the 7 is significant, again, because of rule number 1, so I'm not going to write that. The 0 at the end here is significant because of rule number 3, okay? Because rule number 3 says it's to the right of the decimal place, which this 0 is to the right of the decimal place, and it's after a significant digit, which that we know the 7 is significant. And honestly, the 0 in the middle is also significant because of rule number 2, okay? If the 7 is significant and the 0 at the end is significant, then the 0 in the middle is between two significant digits, which makes that significant as well. So that number, 70.0, would have 3 sig digs, okay, compared to the 1 sig dig in just 70. The other thing I want to point out to you that happens sometimes in science is that, whole numbers kind of pose a problem for us because, like, what if we do actually mean exactly 70, but not to the point, like, what if we want that ones place and we're not rounding, but we don't want to go all the way to the tenths? You might see, like in a practice problem or something, that you'll see the number 70 with a decimal point after it, and that's it, like no 0 following that decimal point. And that's kind of like the little workaround that scientists use to tell you, like, well, we do mean 70 exactly, but we're not committing to the tenths place, so you can count on the ones spot, and that'll give us 2 sig digs, but we're not going to give you a third. Okay, so I know that's a little non-traditional in terms of how you learn about it in math, but that's how it works. All right, the next one. Okay, you have, so if we look at this, oops, it's hard to write on this program. All right, we have 0.00302, and we have 0.0030200, okay? Here's what I want to point out to you. All right, first of all, the 3, the 0, and the 2 are definitely significant, right? Because the 3 and the 2 cover rule number 1, which is they're not 0. And then the 0 between those is rule number 2 because it's between two significant digits. Looking over at the right example, again, that 3, 0, 2. However, the zeros to the right are also significant because they, these 2 zeros right here are rule number 3, right? They are to the right of the decimal, but they are also after the first, or after a significant digit. Now, the zeros on the left of both numbers are not significant because of rule number 4, okay? They are considered placeholders, all right? And what that means is that they're just hanging out in a spot, letting you know what value, like what place value your significant digits are in, all right? So for example, and I just crossed it out, so I'll rewrite it. This 3 is in the 1,000th spot. And the way we know it's in the 1,000th spot is because we have zeros in the tenths and the 100ths place, okay? And so that's really where that's useful. That's why those zeros to the left are just considered placeholders. And the other thing that I would show you to sort of cement the fact that they're placeholders is that you could write this in scientific notation and you would not need those zeros to the left at all. Okay, if you wrote this in scientific notation, you would just include those 3 digits, which are the significant digits. You would not include the ones on the left. Okay, same thing for the other example in this problem. I just want to point out to you, in case you're wondering this, yes, you would include those zeros that are to the right because they are significant when you write in scientific notation, but you would not have to include the zeros that are to the left, okay? And then, like, finally, what I would say, so let's pretend this wasn't to the right of the decimal. If we just had the number 302, for example, okay, you would not put zeros in front of that. And you know it. Like, and if you saw zeros in front of there, you would know, like, okay, well, I don't really need those. All right. Rules for doing calculations with SIGDIGs. All right. What comes up most often is multiplication and division. Okay. Because that's really the bulk of what we do. It's just important for you to realize that the maximum number of SIGDIGs in your final answer can't exceed the number of SIGDIGs in your least precise piece of data. Okay? The other thing to know, because we do so much using dimensional analysis, or fences as I like to call it, is that conversion factors, which is what we put into the fences typically, are not considered pieces of data. They're just conversion factors. Okay, so if you look at this example, like, what is the density of a sample of water with a mass of 200 grams and a volume of 199 milliliters? Well, you know that density is mass over volume. So 200 grams divided by 199 milliliters gives you 1.005 blah, 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 blah in your calculator. Okay? SIGDIG wise, you don't get all those digits. You have to look at the data. The mass only has 1 SIGDIG. The volume has 3. Because the mass only has 1 SIGDIG, you're limited to using 1 SIGDIG, which means you can only report a density of 1 gram per milliliter. Okay? And then lastly, addition and subtraction, which probably comes up most often in terms of averaging. Similar situation, but instead of counting SIGDIGs, you're looking for decimal place values. So your final answer can only go to the place value of the piece of data with the least precise place value. So for example, if you look at these measurements down here, this goes to the tenths, this goes to the thousandths, but this only goes to the ones, which means when you average these 3 pieces out, you're whatever average, like, so if you add them up and divide by 3, you're going to have to round to the nearest whole number, because this piece of data is a whole number and you can't exceed the place value of your least specific measurement. So I think I put it in my calculator earlier, but I don't have it in front of me. I'm pretty sure that your final answer for that one would be 37 as the average, because that would be the closest whole number to the answer you get on your calculator.